Good evening, everybody. Welcome to Tibbetts Physics. What is crappinin'? Today we're going to learn about the last energies in the work energy units, and those are kinetic and internal energy. As you can see, we've got a different background here. I'm here making a video at work. I'm not sure what you thought I did, but actually I do work, and I don't sit at home making videos all day long. I actually have a job, and this is my classroom, and we got some sweet paintings in the back. Let me get out of the way. Here's a quick 360. Nice size classroom for physics, I suppose. So, before we get into kinetic and internal energy, let's just quickly summarize the formulas we've learned so far. The first one we have is work is equal to force times displacement, and its units are joules. And then we learned about power. Power is just work over time. And we could expand that to force times velocity, force times distance over time, because that's what work is. And distance over time is velocity, so force times velocity. And its units are watts. And then we learn potential energy of a spring or elastic potential energy. That's 1/2 kx squared. Its units are joules as well. And the last one we learned was gravitational potential energy, PE sub G, and that's just mgh. And its units are also joules. So far, all the units we've learned that involve energy are joules, and power is energy over time or work over time, and that is watts. So let's first define kinetic energy. You may have learned this word before. Kinetic energy, or KE. Okay, kinetic energy is the energy of motion and that's it. So it's the energy of motion. The formula, we're going to develop it, but I'll give it to you right now. The formula for kinetic energy, KE, is 1/2 mass times velocity squared. So 1/2 mv squared. Okay, so we're going to develop this formula starting with work, the formula for work. And work is equal to force times displacement. And we know that force is equal to mass times acceleration. So W is equal to mass times acceleration times distance. And we're going to look at an old distance formula from the first unit. That one is D equals VI of T plus 1/2 AT squared. And let's just say that the object starts from rest. So we'll get rid of VIT. So we're left with D equals 1/2 AT squared. And what we're going to do, we're going to plug this in wherever we see a D in the work formula. So we'll plug it in right there. So now we have work is equal to mass times acceleration times all the junk on the right, 1/2 AT squared. And let's just expand this. So now we have W equals M. Let's put the 1/2. It doesn't matter. M times 1/2. A times A is A squared. And then T squared. And we'll reorganize this a little bit. Work is equal to 1/2 M A squared T squared. Everybody following along so far? Let's look at our original formula of acceleration. So we have another on this side. Acceleration is change in velocity over time. So wherever we see an A, we'll plug in this crap, change in velocity over time. So now we've got W equals 1/2 M delta V over T quantity squared times time squared. So if we expand this squared above delta V over T, we're left with delta V squared over T squared, and our T's cancel out. If we could click here, our T's cancel out. So we're left with work is equal to 1/2 m change in V squared. So work is equal to the change in kinetic energy. So we'll expand it into one formula. Work equals delta KE. Change in velocity is change final minus initial. So if we expand this, it's 1/2 mVF squared minus 1/2 mVI squared. So we have to make sure to square our V's when we're doing this formula. That's the most common error. And we're not squaring the entire thing, just our velocities. And this formula we just developed is 2 in 1. We know the work is change in kinetic energy, which is 1/2 mVF squared minus 1/2 mVI squared. And this is called the Work-Kinetic Energy Theorem. And all that says is, whenever work is done, the energy changes. So in this case, when you're applying a force over a distance, you could either be using it to speed up or slow down an object. In that case, the kinetic energy changes. Or work could be done if you lift an object up, and we learned that last video, that would give it potential energy. So that's the Work-Kinetic Energy Theorem. Okay, so let's do one example looking at the Work-Kinetic Energy Theorem. A 2 kilogram Hot Wheel object, so we know the mass is 2 kilograms, is moving with a velocity of 3 meters per second. VI is 3 meters per second. How much work is required to speed it up to 5 meters per second? So VF equals 5 meters per second. And we just learned that work is equal to change in kinetic energy, which is equal to 1/2 mVF squared minus 1/2 mVI squared. Sorry, excuse me for 1 second, my phone is ringing. America Industries. Who's this? Why are you calling me? How'd you get my number? Okay, please don't call me here again. Thanks. Sorry, that's my mom. Okay. Anyways, so now all I have to do is plug and chug. So work is equal to 1/2 2 kilograms times 5 meters per second squared minus 1/2 2 kilograms times 3 meters per second squared. Again, don't forget to square your velocities. We plug that in our calculators and we get work is equal to 3.5 joules. So now let's combine work, potential energy, and kinetic energy to look at the classic roller coaster scenarios. We've got a roller coaster way up here, goes down and goes up, not quite to the top. And we'll say the bottom is the ground level, and this is the max height. And we'll look at 3 scenarios of the roller coaster. We'll look at here, as it goes down, at the very bottom, and up to the spot right here. So, at the very top, it has maximum potential energy. So, PE equals max. Since it has maximum potential energy, and it's not really moving at the top, kinetic energy equals 0. Now what happens at scenario 2, when it's moving down the roller coaster, what's going to happen to the potential and kinetic energy? Well, the potential energy is getting closer and closer to the ground, the car is, so the potential energy goes down, and the car is being accelerated downward, so the kinetic energy goes up. Now, what happens at the very bottom to the roller coaster carts? The height is 0, so it doesn't have any potential energy. And it's at the bottom, so this is where it's going to be moving its fastest. So its kinetic energy is its max. And then it goes up a little bit to spot number 4. Not quite at the top, but potential energy is increasing because it's getting higher. And the kinetic energy is decreasing because it's getting higher, and its gravity's pulling it down, so that's causing it to slow down. So kinetic energy decreases. We'll look at this next video. This leads us to the conservation of energy. Now, we're looking at a perfect scenario where there is no friction. But what happens when we add friction to the scenario? And that leads us to our last energy. Okay, so when we're talking about friction and how energy is lost due to friction, that's internal energy. So internal energy is the energy that is transferred to heat. In most cases, it's always heat, and it's through the process of friction. Sorry for my sloppy handwriting. So, let's do a little example. I'm going to rub my hands together, and you want to do the same. And as you're rubbing them, you're creating friction, and you notice your hands are getting warmer. As fast as I rub them, geez, it's getting really hot in this room. Oh, there's my special guest, Mrs. Whaley.
Hi, guys.
To help us, to do a little demo for us, Mrs. Whaley is going to play with my balls, and she's going to smash them together to generate some heat. So here's my spare balls.
All right.
And she's going to smash them in between this paper.
Ready, guys? Again?
Yeah, do a lot. Whew.
They smell hot.
And notice all these holes in this paper that the balls generated the heat.
These are some hot balls.
All right, and that's internal energy for you. See ya.